Okay, here we're going to use the z-scores and look at the actual application of standard error, what we've been doing previously. So now we know how to calculate the standard deviations of sample means. In other words, standard error for mean. And we know the shape, we know the spread, and we know the standard deviation, standard error, how to calculate them. And so what can we do with that? That's what we're going to be looking at here. Okay. Because sampling distribution of the mean is usually normal, we can apply everything we know about z-scores and the normal distribution to the sampling distribution of m. For example, suppose I know that the sampling distribution for m is normal in distribution with the expected value of 50 and a standard error of 2. Also suppose that I observe a sample mean from the sampling distribution and that sample mean equals 50.24. I could then calculate a z-score for that sample mean of 50.24. What do you mean by that? Okay, let's look at that. Okay, let's recall my z-score formula. Z-score is like the this is the sample mean. Okay, sample mean minus population mean divided by standard deviation. That's what the z-score formula. So if I treat m as x and treat the expected value of m as mu and treat the standard error of m as sigma, I can calculate the z-score for m as okay. See, z-score for sample mean. Okay, sample mean minus population mean divided by standard deviation of sample means. Okay, that's what it is. But let's look at the actual problem. This make much more sense. So for example, the z-score for the sample mean of 50.24 would be okay, z-score is the sample mean minus population mean divided by the standard deviation of the sample mean, which is 2. So it's just like that. So z-score for my sample mean is 0.12. So I know that sample mean of 50.24 is 0.12 standard errors from the expected value of the sample distribution. So this sample mean 50.24, it's 0.12 standard error. You don't call it standard deviation because it's actually standard deviation, but to distinguish to emphasize that it is actually the standard deviation of a sample means, you use a standard error here. So 1.12 standard errors from the expected value of the sampling distribution, 0.12 standard errors from the population mu. Okay, if you use a z-score, it's like this. It's a 0, and this is 0.12 right here. Okay, let's look at this. Suppose I know that a sampling distribution for m is a normal distribution with an expected value of 50. Okay, and a standard error of 2. Also suppose that I observe a sample mean from the sampling distribution and the sample mean equals 53.92. Again, what that means is that you actually calculated the sample mean then it turned out to be 53.92 in this sample population. I mean, in this sample. What it means by z-score is, it's calculating the z-score of this particular sample mean out of all the samples, all the sample means in the population. Remember, this is just one sample mean, but there are many number of samples, samples, in other words, hence sample means here. See, all these are sample means. If you happen to take this sample and sample mean, which is 50.24, what you want to know is z-score for that. What would tell you, if you get the z-score for this particular value, what you can say is, a particular sample mean. You can also know, percentile. How many percent of means are below this mean? How many percentage of the means are above this, this sample mean? You can know all these things. That's what we're trying to do here. So we use a z-score to figure that out. We can use a z-score table to figure out the proportion here or here. That's what we're trying to do. Why is this so important? We're gonna talk about it later next. Anyway, let's keep doing a calculation. Okay, so example 5. Suppose I know that the sampling distribution is blah 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 blah. So let's calculate the z-score for the sample mean of 53.92. Okay, so that's the actual calculated mean for this sample, right? And so to calculate the z-score for that, or standard error for this, no, z-score for this sample, this particular mean in the sample means, in the distribution of sample means, this in here. Okay, that's 53.92 minus 50 divided by this, right? So 1.96. Okay, the z-score for the sample mean is 1.96. This sample mean is 1.96 standard errors from the expected value sampling distribution. Okay, so what this particular mean was here, 53.92. So majority of the sample means are actually lower than that. It's like one of those outliers, and we can use a z-score to figure that out. Figure out how many the portion of this, the rest of the sample means, So in other words, 1.9, what was that? 96. Okay, was it not 1.96? Z-score was 1.96. So which is, if we calculate the proportion, it's 0.975. Okay, so 97.5% of all the means in this distribution of sample means is actually smaller than this. And here it's going to be 0.025. So 2.5% of the it's only at 2.5% of the entire sample mean distribution is going to be larger than that. So it, you can figure out these sorts of things, we're using this z-score and z-score table. See? Let's keep doing that. Okay, suppose I know that the population distribution of scores on a test, okay, it's a normal distribution with a mean mu of 50. So okay, so it's a population this time, you know. Don't be confused with the previous examples. Okay, and the mu was 50, and standard deviation of the population is 20. And you draw a random sample of 100 people, okay, from the population distribution. What is the probability that the mean of my sample will be greater than 52? So it's like a combination of you know, calculating the standard error and also calculating the z-score using the standard error and figuring out the proportion. You know, so it's like a combination of this time's example and example from the previous video. How do you do that? Okay. First, you need to kind of figure out some of the things, like, okay, so population distribution score distribution. Okay, it doesn't say population is normal, but because the sample size is 100, this is going to be a normal, you know, sample. The sample is going to be a normal distribution, so we can use a z-score to figure things out. Okay, so let's calculate the standard error, because we need standard error to, you know, figure this out. Okay, standard error is, you know, this formula, and the standard error is going to be, okay, standard deviation of population divided by the square root of a sample population. So it's 20 divided by 10, so it's going to be 2. Okay. So it's like this, and let's calculate the z for this. For okay, what we want to know is, you know, we're just picking one sample mean of 52, and what we want to know is, okay, let's see, 52 is about here, right? What we want to know is, you know, what are the chances that the, you know, or how much portion of this distribution is going to be over 52, mean of 52? So I want to know this portion, you know, proportion of this area. And how do you do that? You know, you get the z-score for this and get the proportion for this and the proportion for that. That's how you do. So how do you get the z-score for here? Okay, first of all, what you need is, you know, the mean for this. This is like 50. Okay, so 52 point, what was the 52? Okay, 52. Particular sample mean is 52, so 52 minus 50 divided by standard error is, standard error in this is 2, right? So it's 1. So what it means is that the, you know, z-score for this is going to be 1. In other words, you know, okay, so if you, based on the z table, okay, this proportion is going to be 0.1587. So recap, okay, if the population distribution of scores on a test had a mean of 50 and a standard deviation of 20, and I draw a random sample 100 people from the population distribution, the probability that my sample mean will be greater than 52 is 0.1587. In other words, it's 15%, 15.87%.